the next topic we're going to talk about is strong induction. So we're going to start here with an example. I want to prove that any postage of 8 cents or more can be made using 3-cent and 5-cent stamps. So before we get into the proof of this, let's just try to gain some intuition about how this works. So I know if I have 8 cents, I can make that by doing 3 plus a 5. If I have 9, then I can do a 3 and a 3 and a 3. If I have 10, I can do a 5 and a 5. So far this seems like it's going to be true. 11, I can do a 3 and a 3 and a 5. 12, I can do a 3 and a 3 and a 3 and a 3. 13, I can do a 5 and a 5 and a 3. All right, so we can keep going like this and hope that we can always figure it out. But what I want to try to do is look for a pattern here. So if I know how to make some amount of postage, how does that help me figure out the next one? And we can see that we're not going to actually be able to get directly to that next one. But if I know how to make 8 cents, for example, then I should be able to get to 11 cents because I use that same 8 plus an additional 3. If I know how to make 9 cents, then I should be able to get to 12 because again, I can use that initial 9 plus a 3. And if I know how to make 10, then I can get to 15 because I have that initial 10 plus that 3. So once I have a certain amount of postage, I can always go 3 more than that. So this gives us an idea that I can basically get from n to n plus 3, which is not quite what I want to do in induction. But what we can do is we can change our induction a little bit. We're going to get this idea of strong induction. And that's going to allow us to not just use the fact right before. Right, so if I'm trying to prove 14, it's not helpful to know that I can make 13, but it is helpful to know that I can make 11. So instead of knowing just the stuff before, we're going to know everything that comes before. And that set of everything that comes before is going to be enough to do what we need to. So let's go ahead and talk about what a strong induction proof looks like, and then we'll come back to this example and see how we can actually prove this. So let's look at this outline for a proof by strong induction. So we're still going to be proving a statement of the form for all n, and in particular for all n in the set of natural numbers. Some p of n, right, is true. I don't really need to say is true, but I can. So I'm trying to show some statement p of n is true for all n in the natural numbers. So we're still going to prove for the first statement. So we're still going to prove that p sub 1. But potentially, depending on how our inductive step works, we might need several more base cases. So we'll talk about that as we go through some of these proofs to sort of figure out how many base cases I need. And then we're going to prove the statement of the form, oops, let me fix this over here, of the form p sub 1 and p sub 2 and all the way up to p sub k. We're going to prove that implies p sub k plus 1. So I'm not just going to use the statement before, I'm going to use all of the statements that come before together. Right, so this is like, if we think back to our bag example, it's like saying the number 1 is in the bag. And for every n, if 1, 2n is in the bag, then n plus 1 is in the bag. So I'm not going to just be able to say, oh, well, if 1 is in the bag, 2 is in the bag. Well, I guess I can. I'm not going to be able to say if 2 is in the bag, 3 is in the bag. But I will be able to say if 1 and 2 are in the bag, then 3 is in the bag. But right, that's still going to give us every number being in our bag, because 1 is in there, so 2 is in there. And then 1 and 2 are in there, so 3 is in there. And then 1 and 2 and 3 gives us 4. And 1 and 2 and 3 and 4 gives us 5, and so forth. So we're going to sort of set up the same way. So we'll say something like we're going to proceed by strong induction We'll have our base cases, because there might be more than one here. And again, we'll see why we might have more than one. And then I'll have the inductive step. And now in the inductive step, I'm going to assume for some k, so for k and n, p sub 1 and p sub 2 and p sub k is true. Right, so this is going to be kind of hard, but I could say something like for j less than k or equal to p sub k, p sub j is true. So it's true for everything up to some point. And maybe I'm going to have a lower bound on my j here, which may or may not be 1. Okay, so again, let's see this in an example. I'm going to assume that p sub j is true, and then I'm going to show that the next one, p k plus 1, is true. Okay, so now let's go back to this proof that we can make any postage of 8 or more cents using 3-cent and 5-cent stamps. We're going to proceed by strong induction. So the first thing I need is my base case, or my base cases. And I'm going to go ahead and just have one to start, and we'll come back later and see if we need some more. So I'll leave some space. So let's say, well, we just want to say that we can make 8 cents. So maybe we can say n is 8 here, because that's the lowest number I want to make. So then I can just say how we can make 8 cents. We can make 8 cents using 5 cents plus 3 cents. Okay, leave some space. Now let's do our inductive step. So assume for some fixed k in n, we know how to make, I want to assume I know not just how to make k cents, but every number from 8 up to k. So we know how to make j cents for j between 8 and k. And now I want to consider k plus 1 cents. I want to show how I can make k plus 1 cents. So k plus 1, that's equal to something plus 3, because I know I want to pull off that 3 cents. So that's equal to k minus 2 plus 3. So as long as this k minus 2 is something that I know how to make, then I can say, oh, by the inductive hypothesis, I know how to make k minus 2 cents. So then I know how to do that. Right? So over here, I need to show that k minus 2, the number of cents I want to make, is between 8 and k. Right, so for example, it's like saying I want to try to make 15 cents. So I subtract 3 from 15 to get to k minus 2 is 12. And as long as I know how to make 12 cents, then I just add that 3-cent stamp and I'm done. But I'm going to run into trouble, right? Let's say my k plus 1 was something like 10. So if I'm trying to make 10 cents, I go back to k minus 2. Now my k minus 2, I've done equals here before, so I'm going to fix that. Now my k minus 2 would be 7, and I don't know how to make 7 cents because that's too small. So I need this k minus 2 to be less than k, that's fine, but also bigger than 8, which tells me here, right, if I add 2 to both sides, that this k really needs to be bigger than, how do I add 2 to 10? Add 2 to 8. It has to be bigger than or equal to 10. So I can really only start with my k being 10 and then go up from there. If I'm starting at less than 10, I can't subtract 3 right, and go backwards to get my k plus 1. So here I need to say assume for k and n with k greater than or equal to 10. We know how to make j sense for j between 8 and k. So when k is 10, I know how to make 8, 9, and 10. When k is 11, I know how to make 8, 9, 10, and 11. When k is 12, I know how to make 8, 9, 10, 11, 12. Now I'm going to consider k plus 1 sense. So then I know, let's do this kind of in here. Since k is bigger than or equal to 10, k minus 2 is bigger than or equal to 8. So k minus 2 is between 8 and k, which means we know how to make k minus 2 sense. So consider how, well, let's see. Now I just want to put in that we know how to make k minus 2 sense. Oops, deleted that. If I know how to make that k minus 2 sense, we know how to make k minus 2 add that 3-cent stamp to make k sense. Oops, k plus 1 sense. So now I've said how to make k plus 1 sense. So that's going to be the end of my inductive proof. I showed how to get from everything up to k plus 1. Let me actually make it look like a k plus 1 here. So then I can go outside of my inductive proof and say, by strong induction, we can make any amount of postage greater than or equal to 8 cents. Okay, so that's almost our entire proof. But now we have to think, okay, how does this proof actually work? How do I make 8 cents? Boom, it tells me how to make 8 cents in my base case. How do I make 9 cents? Well, I don't know how to go from 8 to 9 here because I can only do my inductive step if I'm starting with something already bigger than 10. So when k equals 9 and k equals 10, I can't get those from my inductive step. So I actually have to include those in my base case. So 9 cents we saw was using 3 cent, 3 cent, 3 cent. 10 was using 5 cent, 5 cent. So now I have these 3 base cases, right, which makes sense because that's kind of where we started and we added 3 cents to everything. And then my inductive step starts at k greater than or equal to 10. So once I have all of the k's from 8 to 10, then I can go up and get the ones after that. So there's definitely some weird details we have to consider here. So next we're going to see an application of strong induction on graphs. So I've got some definitions here. So the type of graphs we're going to be talking about are collections of vertices and edges where each edge connects two not necessarily distinct vertices. So let's think about what that means. Here when we visualize these graphs, we're going to think of the vertices as points and the edges as lines between them. They don't necessarily have to be straight lines. And then each edge connects two not necessarily distinct vertices. So an edge is just going to go from vertex to vertex. They could run into each other, right? But I'm not going to necessarily have a vertex between those. I could also have an edge that connects a vertex back to itself. So I could have that little loop there, right? These are all allowed in graphs. Now the next definition says that a cycle is a sequence of distinct edges that ends where it began. So this isn't really the best definition because we haven't defined what it means to have a sequence of edges. So we can go ahead and define that. So when I have a sequence of edges, to go from one edge to the next, one edge has to end where the next edge begins. So they have to be connected by that vertex. So I can go from edge A to edge B to edge C to D to E. And that's going to be a cycle because I got back to where I began. It has to be distinct edges. So I can't say, oh, go from A to B and then go back on B and then A, right? A, B, B, A is not distinct edges because I used B twice and I used A twice. So that's not allowed as a cycle. But other things are allowed. So let's draw maybe some graphs here that have a couple of different cycles. So then I can ask lots of different questions. I could say, how many cycles are there in the graph? I can say, what are the cycles? What's the biggest cycle? What's the smallest cycle? But we can also say, what does it look like to have a graph that has no cycles? So a graph that has no cycles is called a tree. So I can draw an example here of a tree. That's just a graph that has no cycles. And in fact, it's a connected graph that has no cycles. So I can't just think about a graph where I have this sort of tree over here next to this tree over here, and then think of those all as just one graph. So in general, our graphs don't have to be connected, but we usually think of them as being connected. Okay, so now let's look at this tree. Let's draw a whole bunch of different trees here. If you have a collection of trees, so a graph which is made up of several trees, it's called a forest, because obviously it's called a forest. But I'm thinking of these as different from each other. They all happen to have, well, let's see, this guy has 4 vertices and 3 edges. This one has 5 vertices and 4 edges. And this one also has 4 vertices and 3 edges. It's really just the upside down version of that one. I could have 1 vertex and 2 edges. This one has 9 vertices. 8 edges. All right, so we might start to notice in all of the examples I've drawn so far, when I have 4 vertices, here I have 3 edges, it looks like the number of edges is always 1 less than the number of vertices. So we can make a conjecture. A tree with n vertices has n minus 1 edges. So I encourage you to try to go ahead and prove or disprove this conjecture. See if you can come up with a counterexample to disprove it, or see if you can come up with a proof. And we'll prove this on the next slide. Okay, so the proposition we want to prove is that a tree with n vertices has n minus 1 edges. So let's think about how we could prove this. So let's say I start with a tree. And whenever I'm thinking about doing an inductive proof, I usually sort of think about it backwards. So I think about trying to prove something for my bigger number and think about how I can prove that based on the stuff that comes before. Right, so if I have a tree with n plus 1 vertices, that's going to be the thing that I'm trying to prove in my inductive step. I want to think about how I can reduce that down to a simpler tree. Now I know if I have this tree with n plus 1 vertices, we could go ahead and think about what happens when we remove a single edge. So I'm going to remove this edge here. And think about what I get left. Well, now it's going to be disconnected, so I'm going to get 2 different components. But my claim is that both of those should be trees because they can't have any cycles, right? Because if they did have a cycle, then the original graph would have a cycle, so that wouldn't be a tree. So I'm starting with that tree with n plus 1 vertices. I remove an edge, and I should get 2 trees. But these trees both have smaller number of vertices. So now they don't necessarily have n vertices, because I just sort of removed an arbitrary edge in the middle there, but they should have a smaller number of vertices. So if I've assumed every single one of them has of smaller size has the right number of vertices, then I'll know that this one does. So let's say I have maybe m and l vertices with m plus l is equal to that n plus 1. Well, then m is going to have m minus 1 edges. L is going to have L minus 1 edges. So together, they should have M plus L minus 2 edges. But then that's the M plus L is that N plus 1. I subtract 2 to get N minus 1 edges. But then there was the initial edge that I removed. So that gives me that N edges, which is what I want for N plus 1 vertices. Okay, so that was our background work. We sort of figured out what the details should look like. So now let's see if we can prove that. So I'm going to start with my base case here. We'll assume the graph, well, the tree, I guess. Assume the tree has one vertex. So I just have the single vertex here. Because there's only one vertex, if I added an edge, that edge would have to start and end at that vertex. So that edge would actually create a cycle with itself, because that would start and end at the same vertex. So since any edge creates a cycle, the tree must have 0 edges. And then, so one vertex has 0 edges, which is what we need to prove for that base case. Okay, so now let's do our inductive step. So we're going to assume for all trees up to n vertices, so when you have any number m between 1 and, let's say, k, a tree with m vertices has m minus 1 edges. And let me go ahead and use a different letter here because I want to use the m in the role I used it in my scratch work. So I haven't used the letter J yet, so let's pop in a J there. Put it here as well. So as long as J is a some number between 1 and K, I'm going to assume if it's a tree with J vertices, it has J minus 1 edges. So now I can consider a tree with K plus 1 vertices. So I don't know anything about that yet because my assumption only goes up to K vertices. What am I going to do with this tree? I know it has some edges because if it didn't have any edges, then it would be disconnected. So I can remove one of those edges. When I remove one edge, then I must have 2 disconnected components. So we actually have to prove why that's true. So if the graph is still connected, let's add a couple little details here. Well, okay, so what if it's still connected, right? So I have this edge that I removed, let's say some vertex A and B. If it's still connected, there must be some way to get from A to B, but that would mean that there must have been a cycle before, because then there would have been another way to get back. and that would have given me a cycle. So if it was still connected, then it must have had a cycle, and that's a contradiction. So I can't have two paths from A to B, because then I get that cycle. So when I remove an edge from A to B, I must get a disconnected graph. Okay, so we get two graphs. Neither can have cycles, because then the original would have a cycle. So both must be trees. And they're going to have, let's say, M and L vertices, where the sum of M and L is M plus 1. So I'm splitting it up. But now, because the sum of them is N plus 1, each must have at least one edge. So I know that M and L are less than or equal to K and bigger than or equal to 1. Thus, by our inductive hypothesis, we get that one has M minus 1 edges and the other has L minus 1 edges. So overall, there are M plus L minus 2 edges, plus the one removed edge, is M plus L minus 1, which is equal to, remember M plus L was equal to N plus 1, so that's M plus 1 minus 1, which is N edges. So what did we prove? We proved if you have a tree with K plus 1 vertices, oh no, my K became an N at some point. Let's fix that. That should have been a K. Ooh, I left that as a K, that was good. Then I should have just had a K here and a K here. So I've got K plus 1 vertices, K edges, so then I'm all set with my inductive step. Now, right, this inductive step actually works going from 1 to 2. So I take 2, I remove an edge between them. Now I have 0 edges, 0 edges, plus that one removed edge. So I don't need extra base cases in this one. So I can just write my conclusion sentence. Right, so by strong induction, we can conclude that a tree with N vertices has N minus 1 edges, which is what we wanted to show.